Bismillahirrahmanirrahim. Assalamu alaikum, students. So, in today's lecture, we're going to discuss the forces of, let me write it clearly, forces of constraints. Well, let me write constraint. This is our today's topic. Now, what is a constraint? For example, if I have a simple pendulum, now you know the simple pendulum consists of a point mass suspended by an inextensible and massless cord. So, and it is allowed to move in a vertical plane, allowed to oscillate in a vertical plane. Now, let its mass be m and let the length of the pendulum be L. Then you know, if we use Cartesian coordinates x and y, for example, I take origin at this point. This is my coordinate system. Let me use another color. Suppose this is my coordinate system. I take origin, for example, here. So this is x, this is y. So if it is my coordinate system, it appears that there are two independent variables in the system, x and y. But they are not independent, as you know. There's a constraint. What is the constraint? This x will change as the pendulum oscillates. Y will change as the pendulum oscillates. But at all times, x square plus y square must be equal to L square. X square plus y square must be equal L square, right? Now, when you use this constraint, you see that actually there is only one independent variable in the system, and that we take the angle made by the string with the vertical, that is theta, right? So the variables in the system, which were x and y, if we use the Cartesian coordinates, they were reduced to 1 theta by this constraint. So in any mechanical system, there might be some number of independent coordinates which change with time. So if you impose if there are any constraints in the system, constraints are restrictions which are imposed on these coordinates in the system. So if there are constraints, you impose the constraints, these restrictions in the system, that leads to decrease in the number of independent coordinates, right? Now then we, in physics, refer to the force of constraint. That means the force pertaining to the constraint in question. We want to discuss this idea. So there are two ways to discuss a system in which there are constraints. One is you take all the independent, so all the coordinates, not independent, all the coordinates which appear in the system, then solve for the equations. Once you solve the equations, after that, you impose the constraints in the system, in the equations of motion which you have solved. So if you impose constraints at last after solving the equations of motion in different variables in the system, you have to handle many variables. But the advantage of that is at the end, you can find the force of constraint, the force pertaining to that, the pertaining to the constraint in question. Second thing, when we are interested in only finding the equations of motion, we are not interested in finding the forces of constraint or force of constraint depending on the number of constraints. Then what you do, you at the outset impose the constraints in the system on your variables and reduce the number of variables and solve the equations of motion for those independent variables. So there are two ways. So if I am interested in just finding the equations of motion, I impose the constraints in the system too early before solving the equations of motion. That helps me to reducing the number of independent variables, and situation becomes easier. But if I am interested in finding the force of constraint, then what I do, I take all the variables which are in the system into consideration, find the Lagrangian, find the equations of motion pertaining to that coordinate, those coordinates in question, then impose the constraint in the equations of motion. But that way, I have a plus point that I can find the force of constraint. So let us consider this example. So constraints can have types, they can be holonomic, they can be non-holonomic. For example, this constraint which we have discussed here, x square plus y square is L square, this is a holonomic constraint. So when you have such equalities in constant equations, such constraints are holonomic. They simply reduce the number of independent variables by the number of constraints. For example, if the total number of variables is n and I have one holonomic constraint, then my independent variables in the system will be n minus 1. But in certain situations, the constraints are in the form of inequalities. Those constraints are called non-holonomic. They don't reduce the number of independent variables in that way, because you cannot put those inequalities into the system, right? So we are considering in most of the times the holonomic constraints, which can be simply imposed by using the constraint equations, which are in the form of equalities, and they reduce the number of independent variables. So depending on the number of constraints which are holonomic in the system, you will get smaller number of independent variables. So if you have 10 variables, you have two constraints, holonomic, then your independent variables in the system will be 10 minus 2, that's 8. So sometimes constraints can be mathematically complicated, sometimes they can be simple, right? So whenever a body is restricted to move along some surface or along some wire, so you have some constraint. That constraint will have some mathematical form, and that constraint, corresponding to that constraint, you can talk of the force, that is the force of constraint. So let us consider an example to understand it further. Let me use another color. I will use red. So we will consider an example. For example goes like this. consider the setup of a particle sliding of a fixed frictionless frictionless hemisphere of radius r. Let me draw a simple figure. I will change the color. Let me use this green. So I have some hemisphere with radius r. Its surface is fixed and is frictionless. Now, a particle is sliding across the surface. So at some time, this particle having mass m is at the location shown, and the line from this point O, let me call it point O, is making angle theta at that time. Let me write it properly, this angle theta. So this is my angle theta. This is angle theta. And this particle is going along this surface. It is constrained to move along the surface of this hemisphere. Now we are interested in first finding the equations of motion. So we will use two ways. First, we will find the equations of motion for this particle which is sliding off this fixed frictionless hemisphere of radius capital R, and we will not bother to find the force of constraint. Then in second case, we will find the force of constraint, right? So let us say that we are concerned only with finding the equation of motion for theta, because it is the theta which changes with time, and that dependence of theta on time will give us how this particle will move in time, right? So everything we will write in terms of this theta. Now the constraint here is that the radial distance from the point O, which in general I call small r, is constrained to be the capital R, because the radial distance of the particle from O as it goes along the surface of this hemisphere will always be capital R. So my constraint is small r is equal to capital R. This is my constraint. Small r is capital R. Small r is the radial distance from O of the particle of mass m, right? So what is the kinetic energy of the particle? Let me write that. The kinetic energy of the particle as theta changes with time is simply half m r square theta dot square. Understand it? Small r is capital R, where r is the distance of the particle from O, m is its mass. So what is half mr square theta dot square? It is actually the rotational kinetic energy of the particle about point O. R square is moment of inertia, and theta dot is the rate of change of theta, that is the angular velocity of the particle. So half mr square theta dot square is its kinetic energy. What about the potential energy of the particle? The potential energy of the particle is due to gravity. Gravity has a role. So if I take the zero of potential energy at the bottom of the hemisphere, then the potential energy of the particle V is equal to mgr cos theta relative to bottom of the hemisphere. So if potential energy at O is taken as 0, then the potential energy at any theta is mgr cos theta, because it is mgh. R cos theta is actually the height of the particle when it is having angle theta with the vertical. Then r cos theta is its height from the bottom. So mgr cos theta is simply potential energy of the particle relative to bottom of the hemisphere or relative to point O. Therefore, what is Lagrangian of the system? Lagrangian of the particle, Lagrangian is simply T minus V, which is half m r square theta dot square minus mgr cos theta. We name it first. This is the Lagrangian of the particle. Half m r square theta dot square minus mgr cos theta. So we can find the equation. In theta, there is only one coordinate, that is theta, for which we have to solve the Euler-Lagrange equation of motion. So let us do that, right? So incidentally, when I write x square plus y square is equal to L square, I have to take origin here. I think I should clear it. Where is this? Let me get my, where is eraser? I think here is eraser. So let me write it properly. Let me get my pen back. This is my pen. So origin of the coordinate I take here. Then this is y. This is x. Right? This is my y-axis. Then the constraint is x square plus y square is L square. So this is the correction here. So now L is equal T minus V is the Lagrangian. So let us find now the Lagrange's equation of motion. Now, using Euler-Lagrange equations of motion, so I have for theta dou L by dou theta dot, then I have take its time derivative, equate that with dou L by dou theta, right? So from figure, let me from the Lagrangian first find dou L by dou theta. My dou L by dou theta is simply mgr sine theta. See the Lagrangian. When you differentiate this with respect to theta, first term has no dependence on theta. In second term, you have minus mgr. When you differentiate cos theta with respect to theta, it will be minus sine theta. So overall, it will become plus mgr sine theta. So it is my dou L by dou theta. Then I find dou L by dou theta dot. So when I find dou L by dou theta dot, that will turn out to be m r square theta dot. M r square theta dot, check it. Second term has no dependence on theta dot. First term has, so it half mr square. Theta dot square is differentiation with respect. Theta dot is 2 theta dot. 2 will go out. So it will be mr square theta dot. Then I have to find the time derivative of this. That means I have to find d by dt of mr, it's capital R. It is here m r square theta dot. I have to equate it with dou L by dou theta, which is mg r sine theta, right? This is separate. mgr sine theta, it is mr square theta dot. So it will become simply m r square theta double dot is equal to mg r sine theta. Mr square theta double dot is equal to mgr sine theta. So m will cancel out, one r will cancel out. I will get the equation of motion. Let me change the color. I will use now red. So my equation of motion will be simply theta double dot is equal to g by r sine theta. This is my equation of motion. Let me name it equation 2. Theta double dot is g by r sine theta. So this equation gives me how this mass is going to move along this fixed frictionless hemisphere of radius capital R, which is constrained so that its radial distance small r from O is always capital R being the radius of the hemisphere. So we have found the equation of motion, but we don't know about the quorum of the force of constraint. The force which is provided by the surface of the hemisphere which is the force will be, we know it will be the normal force, it will be perpendicular to the surface at all positions of motion. We don't know its form. We know, we have only used the constraint and solved the equation of motion. Now in second case, we want to know, we want to figure out the form of that force. We want to find the force of constraint. So let us do that now. In that case, what we do, we need to understand one thing. When this mass moves across the surface of this hemisphere, what will happen actually, it will sink a bit as it moves along the surface. Why it will sink? The surface, you can assume that the surface of the sphere is made of atoms or molecules which are connected by springs. Springs representing the intermolecular or interatomic force. Now, the force constant of those springs will be large because it is a solid sphere. So, when this mass is pulled by gravity downward, so it actually sinks a bit into the surface. Then it is squashed up because those springs, those interatomic forces will recoil. They will not allow this mass to sink to any extent. So it will be squashed up. That is the normal force. That is the force of constraint. Right? That means in general, the distance, radial distance of the particle from point O, from the bottom of this hemisphere, which is small r, will not in general be capital R. If we take the general situation into consideration. Now we take that situation. So in that situation, as this mass goes along this surface of the sphere, its radial distance from point O will also keep on changing as it sinks into the surface, comes back, sinks into the surface, comes back, and this way it moves along the surface. So our variables, our coordinates, which will change with time, will be two. They will be r and theta, not just theta. See, if I impose constraint in the first place and find the Lagrangian, then my small r is capital R. I have only one variable to deal with. So my Lagrangian becomes simpler, equation of motion becomes simpler. But when I take the real picture into consideration, that will help me to find the force of constraint. You will see. So what I am saying in reality, what will happen as this mass goes along the surface of this hemisphere, it will sink, come back, sink, come back. So its radial distance from the center will not always be capital R. It will keep changing in time, and theta will be also changing in time. So I will have two equations of motion, one pertaining to change in small r and second pertaining to the change in theta with time. So let us do how this potential corresponding to the force of constraint will change. Let me draw the picture. So if I want, if this is small r, it is the radial distance from the point O, from the bottom of the hemisphere. Let me use another color here, blue. So this potential will be very steep. This will be the form of the potential pertaining to the force of constraint. Let me use red color again. So at this point, Small r is capital R, that is you are on the surface. So this is V of R. What is it? It is the potential energy. Let me write it. Potential energy, or which we simply call potential, corresponding to the of force of constraint. So as small r becomes greater than capital R, then what will happen? We are outside the surface. That is not our discussion. Our discussion is when R is maximum capital R. So at that situation, this potential has a steep change with R, because we said that it's a solid sphere and we can assume that its atoms or molecules are connected by springs which have large force constant, right? So this is representing or depicting the potential or potential energy corresponding to our force of constraint provided by the surface of the hemisphere. So when I take this into consideration, when I take the variation of r and theta into consideration, let me write it real picture. I will just clear it. I will write real picture. So in real picture, r and theta change with time. Change with time, right? Now, in this situation, when I take the variation of r and theta into consideration with time, what will be the form of my Lagrangian? Now, the Lagrangian will be like this. It will be half m r dot square plus r square theta dot square minus mg r cos theta minus v of r. I call it equation 3. This is my equation 3. Half m r dot square plus r square theta dot square minus mgr cos theta minus v of r. In this situation, in this real picture, we have not imposed the constraint yet, because we are taking the radial distance of the particle from point O to change with time. We're not taking small r is equal to capital R. So see the Lagrangian. First term is kinetic energy, that has two parts. One is half mr dot square. This is the kinetic energy pertaining to motion of the particle along r. As I told you, it will sink and come back, sink and come back as it goes along the surface. So in radial direction, it is moving. So r dot is velocity in the radial direction. So the first term is the kinetic energy pertaining to its motion along r, that is that sinking process. And the second term is simply its rotational kinetic energy about point O, half m r square theta dot square. Theta dot is the angular velocity. Mr square is its moment of inertia. So half mr square theta dot square is its rotational kinetic energy. Mgr cos theta is simply potential energy, because we are taking it relative to the bottom O of the hemisphere. R cos theta is its height. Then V of R is the potential energy pertaining to the constraint force, right? Now we want to find the equations of motion now, taking this Lagrangian into consideration. So now we have two variables. One is theta and second is R. So let me write now the Euler-Lagrange equations. So Euler-Lagrange equations of motion are. First I will write for theta. For theta, I have to do dou L by dou theta dot. Then I have to find its time derivative. Then I have to equate that with dou L by dou theta. This is the Euler-Lagrange equation in theta. Dou L by dou theta is equal to d by dt of dou L by dou theta dot. So let us do. If you see, it is easy. Dou L by dou theta is simply mgr sine theta. mgr sine theta. In the Lagrangian, there is theta dependence only in second term, that is minus mgr cos theta. When you differentiate it, a cos theta differentiation is minus sine theta, it will become plus. So mgr sine theta is our dou L by dou theta. So let us find dou L by dou theta dot. Dou L by dou theta dot is, that is mr square theta dot. mr square theta dot, check it. mr square theta dot. Why so? Because there is only one term which contains theta dot, that is half mr square theta dot square. Rest terms are independent of theta dot. So differentiation of theta dot square is 2. Theta dot 2 will cancel out. You will get mr square theta dot, right? Then what I have to do, I have to find its time derivative. Time derivative of dou L by dou theta dot, which is mr square theta dot, and equate it with dou L by dou theta, which is mg r sine theta. mgr sine theta. Now here you have to check r and theta are both changing with time. Therefore, you have to use the product rule in the left side. So when I do that, I will get this. I will get mr square theta double dot plus 2m r r dot theta dot. Right side I have mg r sine theta. I will name this equation as 4. Let me check the equation number. So this is my equation 4. mr square theta double dot, when you take r as constant, differentiate with respect to time theta dot. In second term, you are differentiating r, right? It become 2r r dot, and m theta dot is attached. So it is 2m theta dot r r dot, right? Now we will find the Euler-Lagrange equation for r. So for R, let me use another color. For R variable, I have to find dou L by dou R dot, then differentiate that with respect to time and equate that dou L with dou L by dou R. So d by dt of dou L by dou R dot is equal to dou L by dou R. When you do it, I will write the result. You will check it at home yourself. When you do it, you will get this. M, let me adjust my pen. And I will use another color here. Green. So you will get this. M R double dot is equal to M R theta dot square minus mg cos theta minus dv by dr. I name this equation 5. So you have home assignment here. I will write, check it, check this at home. Take the Lagrangian, find dou L by dou R dot, find dou L by dou R, then use Euler-Lagrange equation d by dt of dou L by dou R dot is equal to dou L by dou R. So when you get it, it is mr double dot is equal to mr theta dot square minus mg cos theta minus dv by dr. Here you will have actually partial derivative of v with respect to r, but there is only one variable on which v is depending, that is r, so you can equate it to the total derivative. So there is no issue. So see, when I take the real picture into consideration, I am not imposing the constraint, then I have two equations of motion, one in r and second in theta. But when I, at the outset, start with the restriction using the constraint small r is equal to capital R, then I have just single equation. Things were easier. But there was no way to find out or figure out the force of constraint. Now I have a way to figure out the force of constraint. See. Now I will apply constraint in equations 4 and 5. Applying now the constraint. Applying now the constraint. Small r is capital R. If small r is capital R, that means then r is not changing with time. So its first order derivative with time is 0 and its second order derivative is also 0 with time. When we use these condition in 4, using in equation 4, that is this equation. So when you use r dot and r double dot is equal to 0 in equation 4, this term will go. Then what you will get? You get simply theta double dot is equal to g by r sine theta. That is equation second. So when I use this constraint condition r dot and r double dot is equal to 0 in 4, I will get theta double dot is equal to g by r sine theta. See, this term will go, then small r is replaced by capital R, 1 r will cancel, m will cancel, you will get the equation 2 back. Theta double dot is g by r sine theta, right? Now, from equation 5, using in equation 5, what you get? Using in equation 5, so when you do that, what you get minus dv by dr at small r is equal to capital R. We're restricting small r to be equal to capital R is equal to mg cos theta minus mr theta dot square. I named this 6. mg cos theta minus mr theta dot square. C, go to equation 5. I restrict here r double dot is 0, so this term is 0. Then these two terms I take to left side, one will become mg cos theta, second will become minus mr, small r is capital R, constraint we have imposed, theta dot square is equal to derivative of v with respect to r, but at small r is equal to capital R. What is that? What is that? mg cos theta minus mr theta dot square. This is the simply the constraint force, because negative derivative of potential energy or potential with r is the force. So we were in search of this. This is my force of constraint. This is my force of constraint, right? So it depends on theta and theta dot. So my force of constraint, which is the normal force, which is minus dv by dr, is the force of constraint which is applied in radial direction, is simply, I will write it this way, Fn of theta, theta dot, it depends on theta and theta dot both, is mg cos theta minus mr square, r theta dot square. We name this 7. mg cos theta minus mr theta dot square. So we have been able to find the force of constraint. Instantly, this expression for force is valid only if this force is greater than 0. Because if it is equal to 0, then mass will not slide along the surface in question. We have to take that, we are taking that situation into when this force exists, that when mass is going along the surface of the hemisphere, right? Now, I hope the method is clear to you. See, what is the method? You can apply same method to the constraints of other kinds. So what is the method? See, we considered first the motion of this mass along the hemisphere, we applied the constant at the outset, at the start. That reduced our number of variables in question. We had only one variable which changes with time, theta, and we had only one Euler-Lagrange equation in theta. Lagrangian was simple. But from this picture, we cannot figure out the force of constraint, right? So when we are just concerned with the equation of motion, we are not interested in finding the force of constraint. We do this way. We apply the constant at the start and reduce our number of variables, find Euler-Lagrange equation. But if we are interested in finding the force of constraint, then we don't apply the constraint at the start. What we do, we take the potential corresponding to the force of constraint into consideration, and we take all the variables which might change with time into consideration. So we have more number of equations. Once we get the equations pertaining to the variables in question, then we apply, after solving for the equations of motion, our constraint. What is the plus point? We get that equation back which we got using our previous method, but in addition to that, we got the expression for the force of constraint. So this is the method. So I will give you a simple homework. This is all for today. Another homework, when was that assignment you have to check? So another homework is this question. Check whether the force, let me use another color, F is equal to YZ I cap plus ZX G cap plus, let me write this G cap clearly, G cap plus XY K cap is conservative or not? Is conservative or not? This is another homework. F is equal to YZ I cap plus ZX J cap plus XY K cap is conservative or not. So this is all for today. Go through all the lectures. Don't waste your time. Make a notebook out of these lectures that will be helpful in your examination. And don't forget to like, share, and subscribe my channel. If you have queries, you can comment in the comment box. Thank you very much. God bless you. Assalamu alaikum.